What's up, everybody? Welcome to Danger Person Code. In this video, we're going to be tackling merge sort. Merge sort is what you would think of as a fundamental sorting algorithm. In fact, when you call dot sort, right, as a method on a Python list, when you want to sort it in ascending order, it doesn't use exactly what I'm about to write, but it does use a derivation of this fundamental algorithm. So basically what this is going to do is it's going to take this array down here that's all kind of jarbled in terms of its order, and it's going to sort it in ascending order. And the way that it does that conceptually, merge sort is relatively simple conceptually. It's just kind of a beast to actually code. So we'll take a look at the code. The code is also something that utilizes recursion. And this is not a proper video on recursion and what recursion is and how recursion actually works. I will mention a little bit about that, but if certain parts of this confuse you, I suggest just kind of maybe take some time and maybe watch a couple videos about recursion, maybe read some things about how recursion and the unwinding process works. But essentially, what merge sort is going to do is it's going to take this list and it's going to break it down into increasingly smaller chunks until we have nothing but a bunch of one single element lists, right? A bunch of lists that only contain one element. And we're going to define a helper function that essentially merges sorted lists with one another in a way that maintains their sorted integrity. Okay, so we're going to take by virtue of that helper function two sorted lists, right? Merge them together into a larger list that is still also sorted, right? And by definition, a one element list is sorted, right? It's trivially sorted, but it's sorted, right? So we're going to break these down into one element lists, and then we're going to recursively feed them, right, into the helper function that we define within the larger merge sort function. Okay. And we're going to build all of those one element lists back up into our final sorted lists and return it. It's not important that you necessarily understand everything about how this is working right now, but I just want to kind of give you the code and just let you see how it is written. Okay, so let's without further blah blah blah, let's get into it. So the first thing I'm going to do is I'm going to define my helper function, and I'm going to call it not Marge, but merge. Okay. So merge is going to take two lists that it will merge together. It's going to take list one. It's going to take list two. All right. And then what we're going to do is we're going to define a couple things. We're going to define two pointers. We'll say P1 and P2. And initially, we'll just set them both equal to 0. Okay. We'll also define a list called combined that we will return at the end of the function. And this is what these two, list one and list two, will be sort of merged into. They'll be merged into combined. Okay, so there we go. And then underneath here, I'm going to define a while loop. Okay, and there's actually going to be multiple while loops in this helper function. All right, and we'll talk about them one at a time. So while P1 is less than the length of list one, and P2 is less than the length of list two. Okay, so we're going to iterate basically P1 along list one. We're going to iterate P2 along list two. And we're going to do a bunch of comparisons down here. We only want to do those comparisons so long as one of these has not gotten to the end of the list that it's iterating along. Once it has, the comparisons end, and another part of the helper function will sort of kick into action. Okay, so while P1 is less than the length of list one and P2 is less than the length of list two, we're going to say if list one at index P1, right? If the value at index P1 for list one is less than list two, P2, okay? If the value at index P1 for list one is less than the value at index P2 for list two, then combined, we will add this value right here, list one, the list one value at index P1, we will add that to combined. And of course, after doing that, we will iterate P1 forward. Okay. Now I'm just going to use an else. So if we have any other situation, so if these two are equal or the value at index P2 for list two is greater than the value at index P1 for list one. Okay. If either of those two are true, then combined, we will append combined with list two, the list two value at index P2. And then we will iterate forward P2 by one. Okay, so this will run, basically, we will just keep doing this, making sure that the smaller value in the comparison gets added to combined first, thereby maintaining the ascending order, right, of the larger uh, merged list, right, between the two sorted lists. Okay. So once we do that, once one of these pointers gets to the end of its list that it's been iterating through, okay, we still want the values that are in the other list, right? So we need to set up something that will complete the iteration for the other list once this ends. All right. So we're going to actually set up two more while loops. They're not going to be very complicated. They're going to basically do the same thing. Okay. But there are going to be two more of them. So we're going to say while P1 is less than the length list one. That looks a lot like it looks up here, but this is the only condition that we're going to define for this. Okay. While this is the case, combined and add to combined. Once again, list one at index P1. And then, of course, iterate P1 forward. So if P2 got to the end of list two first, and there were still P1, right? If there were still list one values, right, left over, this while loop makes sure that they are also appended at the end of our combined list. Okay. Now, in the same way, we make a while loop for the other situation. So while P2 is less than the length of list two, right? We will again add to combined list two at index P2. And then we will take P2 and append it forward. Okay, so this basically just ensures that all the values are appropriately appended to combined between list one and list two in a way that maintains the ascending order between these two. So we should end up, as long as these two are sorted, we should end up with one larger sorted list. And again, this is the helper function that we are going to use to build our single element sorted list back up into a larger sorted list once it has been sufficiently broken down. So at the end of this helper function, we're simply going to return combined. Okay. So I hope that makes sense, right? That's fairly simple enough, I think. Use some pointers, you compare some values, you append the one that's lower. Okay. So moving forward, now we kind of get to the part that has a little bit of recursion. And if you've never dealt with recursive algorithms before, sometimes they can look like sort of these algorithms that don't appear to do anything, right? So recursive algorithm is an algorithm where the algorithm calls itself within the algorithm. Okay. And what it does is it keeps adding itself, right, on different different arguments passed to its parameters, but it keeps adding itself to the call stack. And then once it reaches a base case, once it reaches some situation where uh, the algorithm essentially terminates, right, and is no longer doing that, right, and that is a key element of any recursive algorithm. An unwinding process starts to happen where all of those calls to itself on the call stack start actually getting called and actually start getting executed, right? So that unwinding process is going to actually be the building back up process that eventually gives us our larger list. Okay, if that makes sense at all. It's not important that it completely makes sense at this point. I just want to kind of give you the code, all right, and show you how the code, give you some explanation for what the code is doing. Okay. So the first thing I'm going to do is actually define the base case. So what I'm going to say is if the length of the array, right, up here, if the length of the array is equal to 1, return R. Okay. So basically, once we get to an array, right, once we break down these arrays to equal exactly one element, we will return that array, and all of the code that's about to come underneath this, right, will not be executed. We'll basically we will start the unwinding process once this base case is reached. Okay. The next thing we're going to do is define a midpoint. This midpoint is going to be used to cut our array essentially in half and then call merge on those two halves. And those halves will continuously get smaller and smaller and smaller, right? Until again, we just have those one element arrays. Okay, okay, so we're basically just going to take the length of our array, and with the floor, right, we're going to round down. So to ensure that we always have an integer, we're going to divide that by 2. And that will give us the midpoint of whatever array merge sort has been called on. And then we are going to define left, right, and right. And left is going to be merge sort itself, and this is the recursion part. Merge sort itself called on the array, but sliced. Okay, so the beginning of the array all the way up to midpoint. Okay, and you can see why we call that left. This will be the far left point, the beginning of the array, called all the way up to whatever the midpoint happens to be. And then in the same way, right will be merge sort called on the array, but sliced in the opposite fashion. So midpoint, right, all the way out to the end, to the far right end. So it'll start at this point at midpoint and then go all the way to the end of the array. Okay. And then the last thing I want to do is I want to return merge. This is where merge actually gets called on these left and right components. Okay. And then that is basically it. This is merge sort. The vast bulk of it is just the definition, the defining attributes, the defining logic of this helper function that we call merge. Okay. And let's see if we did our work properly. Okay. After this, we define this. Okay. We define a base case. We define a midpoint. Right. And remember, all the logic here will get called and recalled and recalled and recalled, right, on smaller and smaller chunks of the original list because we are calling merge sort itself within merge sort, right, on increasingly smaller and smaller chunks of the list, and then feeding them into merge so that they can be built back up. Okay, so let's see if what we did just worked. Okay, so we will print merge sort on nums. Let me expand my terminal a little bit so we can actually see. Okay. There we go. We run it again. There it is. Okay. So we've taken this array right here. Okay. And we've put all of these in order 1, 3, 6, 7, 12, 14, 17, 23. Right. We all the ascending order, right, of this, crazy mixed up list, right, has been, reestablished here in the output. Yeah. Okay. We basically just broke these all down into using recursion into smaller and smaller chunks, right? By defining a midpoint and then calling merge sort, right, on just smaller and smaller slices, right, of a smaller and smaller set of lists, and then feeding those slices basically into merge to build them back up into bigger and bigger lists that are sorted. Okay, there we go. Okay, and I hope that made at least some sense. Okay, but here is merge sort in all of its glory. And this will deliver that beautiful, wonderful n log n time complexity. Uh, that is so much better than some of the big O's that you get for some of the the lesser used like bubble sort, for instance. I believe bubble sort is really only used as a teaching implement. Merge sort actually has use out in the world. Like I said, Python for its built-in sort function will use a derivation of merge sort. I believe it's a type of sort that it refers to as power sort, right? It's not exactly this, but it does come from this, right? To some degree. Okay. All right. If you have any questions, throw them up in the comments. Feel free to like and subscribe and follow me in the future for more brutal, savage algorithms.